This video on applications of the quadratic formula and quadratics is for my Algebra 1 students who are finishing up the year and doing such a great job. And I just wanted to share with you how you could kind of do some finishing touches on this week's assignment, and maybe doing an application problem is one way you'll want to finish out the school year for your final project. I'm not sure. So we're going to go through 3 problems, and what I've done here is I went ahead and I went on to Desmos. Now, you do not have to use Desmos graphing calculator to do these graphs, but it's a really nice tool. You can also use just your TI-84 or your TI-84 Plus or any other kind of graphing calculator if you would rather. Okay, so the ones I made here that you see were made with Desmos graphing calculator, and what I did is I went ahead and marked some key points that are y-intercepts and the vertex of our quadratic, and then an x-intercept right down here, so we could kind of talk about what these points mean within the context of the problem. So here is the first problem. A person throws a ball from a height of 6 feet with an initial velocity of 48 feet per second. We're using this formula, negative 16t squared, plus velocity times time, plus S stands for the starting point. Okay, so what ends up happening is this is our equation for the situation. This is our 6 feet with the little person over here. And we see that when we actually graph this quadratic, that right over here we see our 6 foot starting point. Okay, and throughout the examples you're going to see today, you're going to see this negative 16 come up in each of the equations, and that has to do with the fact that we're working in feet, and that's sort of a gravitational constant that happens in our calculation. Okay, so this is kind of a cool formula right here to make note of. You might see that again in the future, either in a physics class or certainly in Algebra 2 and geometry as you move forward. Okay, so let's find out what the question is. It says how long the amount of time that the ball is in the air before it hits the ground. So this is going to be time in seconds along the x-axis, and this is going to be your height in feet along your y-axis. And so we know that the ball reaches its maximum height of 42 feet at a time of 1.5 seconds. Okay, because we're doing feet per second. A little overlap there with my arrow. Okay, so that's what our vertex represents. And then anytime we're talking about hitting the ground is always going to be a height equal to 0. So we've been doing a lot of work with solving quadratics. So you guys have dealt with a quadratic that might look like this: 16x squared plus 48x plus 6. And you have been asked to solve that equation. And for something like this, maybe we use the quadratic formula. You can see right up here, it's kind of started, negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Okay, so you can use the quadratic formula to solve for these places right here and here where your graph is crossing the x-axis. We have done this graphically. So this is the quadratic you're solving. The answers that you are getting are going to be where it crosses the x-axis. So you can see this time right here is given. So we know that the ball hits the ground at time equals 3.12 seconds. Okay. The ball hits the ground. So these are the types of problems you were working on this week. I'm going to do a couple more with you just real quick so that you can see this interpretation kind of again. But hopefully talking through this has given you some ideas about what you might show on your final project, how you might work through the 3 problems that I've asked you to work through for me this week. All right, well, let's move it on up a little bit here. Let's try this one. Okay, here you notice your negative 16 again. That's because we're working in feet. That's going to be your kind of gravitational constant on that. When it says write the equation that you were trying to solve, we're trying to solve an equation where the height is going to be 0. Okay, so it says where h is the height in feet and t is the time in seconds, and the rocket is launched upward from a 160-foot cliff. So here's your 160-foot cliff right over here. That's where it's starting. The equation we're trying to solve, because we want to know when it hits the ground, is actually 0 equals negative 16t squared plus 48t plus 160. And you'll notice that 160 is our starting point that we see right here. Well, graphically, again, I just threw this whole equation into Desmos. Of course, when I throw it into Desmos, it looks like this. I type in y is equal to, and then I just use an x in the place of t. And so when I type it into Desmos, I actually type it in like this, using y and x rather than using h and t, so that might help you guys. It looks like the rocket is going to hit the ground after 5 seconds. So 5 seconds to hit the ground. Now, if the question was asking you what was the highest point that the rocket reached, we could come over here to our vertex and see that the highest point the rocket ever was turned out to be 196 feet. Okay, and that happened at 1.5 seconds. So you want to see how you can use your graph to answer those questions that are being asked. And we have one more. Similar idea here. Again, you can have decimals. Don't be afraid of those decimals. Just type them right into your calculator or into the graphing calculator. The question here is, how long does the apple take to reach your friend? And at what height above the ground does your friend catch it? Your friend catches the apple just as it reaches its highest point. So in this particular question, we're really focusing on the vertex. Again, remember that this axis represents time in seconds, and the other axis is going to represent feet. Okay, again, you see this negative 16 right here. Okay, it's looking pretty good. Looks like this apple was launched from about 0.96 feet above the ground. All right, so here we go. At 1.2 seconds, okay, just put a little add in there. The friend caught the ball at a height. So height caught, and you can see that was 24 feet. height caught was 24 feet. I am not quite sure what situation happened so that this friend could catch an apple 24 feet in the air. I'm thinking the only way that is going to happen is if this friend is, I don't know, bouncing on a trampoline. Let's say that. Okay. I think there must have been a trampoline involved for him to be catching that apple 24 feet in the air. That's pretty high. All right. Hopefully this has helped you guys with kind of how to interpret some of these graphical situations that are applications of quadratics. And I will see you soon.